I think the three I said in my lecture, cornerstones of fault tolerance are fault detection, because you can't do anything unless you detect the fault. If you just don't detect it, you can't do anything. And then fault recovery, you have to do something once you've detected it. And stopping the fault from propagating. You have fault containment, isolation. You don't want your fault there to kind of creep into the system and damage other parts of the system. So you need to build firewalls between things, stop them from propagating. Well, you can do some pure software faults, but I mean, if the whole machine crashes, I mean, I'm talking about the fault tolerance of a system, not of the individual software components. So if the entire computer crashes, you're screwed. So you can't really do fault-tolerant computations on one machine. That's how I'm defining it. So, on several machines.
So at least two.
At least two, yeah. I mean, if you want it very, very reliable, hundreds, and put them in different countries and keep them completely isolated, you can basically make things as reliable as you want by having lots of machines. Apart from if they go into a failure mode that you'd never thought of. So you really do need kind of manual backups and things. You might have thought of everything and then, oh, I didn't think a meteorite might come and sort of knock out all of the computers. So don't be deluded into thinking that it's sort of ultimately fault tolerant. You can only kind of provision it for the faults you think might happen. And then for a large class of things that could happen, you can deal with automatic. But then there's this class of things that you'd forgotten about, and they're very dangerous. A lot of them are similar. A lot of hardware errors can be corrected just by doing it again. So if you read a disk and you get an error when you're reading it, read it again, you might not get an error the second time you read it. And a lot of software is like that. If you do something and it fails, you can do it again, and it'll work the second time. And that's because quite often you're using, say, networking or something underneath where you've missed a message or messages have come in the wrong order. If you try it again, it'll work the second time. So to that extent, they are quite similar. I think it's to raise people's awareness of that it's part of the problem, because the problem is more than just what the system should do when it works. It should also say what it should do in the presence of failures that you could reasonably predict. So if you don't think about that, then and you deliver some software to a customer, and then you say, yeah, but wait a moment, the system is behaving in a way that I hadn't specified, you see. So you really like to know how it's going to behave when it goes outside the specification. You've got a nuclear power plant or something like that, and the temperature gets too hot. It's not supposed to do that. So you really need to say what you're going to do if it gets too hot. You can't say, okay, it'll only work in this temperature range. You must tell. And that's more important for things like if you're controlling a nuclear power plant or air traffic, air control system or something like that. Less important in commercial systems, I guess, or banking systems, more important. You have to analyze the consequences of a failure and add that to the specification. I don't really know of any that have. You see, Erlang was specifically designed for fault tolerance. It wasn't designed for anything else. And Erlang-like frameworks have been ported into different languages, but these are added as extra software layers or libraries, so they don't actually behave in the same way as Erlang. They get the sort of flavor of it, but I don't think there's anything that specifically competes with it. I think it's got its little unique niche there.